Question 1. Benchmark analysis indicates that a new wireless communication system requires robust phase modulation for reliable data transmission in a potentially noisy environment. Which of the following approaches best reflects a professional engineering decision-making process for selecting the appropriate phase modulation technique? Option A. Select a phase modulation technique that offers the highest theoretical spectral efficiency, assuming that advanced error correction codes will compensate for any practical implementation challenges. Option B. Prioritize a phase modulation technique that is simplest to implement with readily available hardware components, even if its theoretical performance in noisy conditions is not optimal. Option C. Choose a phase modulation technique based on its historical prevalence in similar applications, without a detailed analysis of its suitability for the current system's unique operational parameters. Option D. Conduct a comprehensive evaluation of various phase modulation techniques, considering their performance characteristics in the expected noise environment, bandwidth requirements, and implementation complexity relative to the system's specific data rate and signal quality objectives. The correct answer is A. Select a phase modulation technique that offers the highest theoretical spectral efficiency, assuming that advanced error correction codes will compensate for any practical implementation challenges. Explanation. This scenario presents a professional challenge due to the critical nature of ensuring reliable communication systems, especially in applications where data integrity and signal clarity are paramount. The engineer must balance the technical merits of different modulation techniques with the practical implications of their implementation and potential impact on system performance and user experience. Careful judgment is required to select the most appropriate phase modulation strategy that aligns with system requirements and regulatory compliance. The correct approach represents best professional practice because it prioritizes a thorough understanding of the specific application's needs and the inherent characteristics of phase modulation. By evaluating factors such as bandwidth efficiency, noise immunity, and the complexity of implementation relative to the desired data rate and signal quality, the engineer ensures that the chosen PM technique is technically sound and operationally effective. This aligns with the fundamental engineering principle of designing for optimal performance and reliability, which is implicitly supported by professional engineering standards that emphasize competence and due care. Adherence to these principles ensures that the deployed system meets its intended objectives without introducing unnecessary risks or inefficiencies. An incorrect approach that focuses solely on the theoretical advantages of a specific PM scheme without considering practical implementation constraints or the specific application's noise environment would be professionally unacceptable. This failure stems from a lack of due diligence and a disregard for the real-world performance of the system, potentially leading to suboptimal or unreliable operation. Such an approach could violate ethical obligations to provide competent engineering services and could indirectly lead to noncompliance with any performance standards or specifications that the system is intended to meet. Another incorrect approach that prioritizes ease of implementation over performance considerations would also be professionally unsound. While simplicity can be attractive, it should not come at the expense of meeting critical performance metrics. This oversight could result in a system that fails to deliver the required data integrity or signal quality, leading to user dissatisfaction and potential system failures. This demonstrates a failure to exercise professional judgment in selecting the most appropriate technical solution. Finally, an approach that ignores potential interference issues or the impact of nonlinearities in the transmission channel would be a significant professional failing. Phase modulation is sensitive to such factors, and neglecting them can lead to severe signal distortion and data errors. This demonstrates a lack of understanding of the practical limitations and environmental factors that affect signal propagation and reception, which is a core aspect of responsible engineering design. The professional reasoning process for similar situations should involve a systematic evaluation of system requirements, including data rate, bandwidth, noise levels, and desired signal-to-noise ratio. This should be followed by a comparative analysis of different phase modulation techniques, considering their theoretical performance, implementation complexity, and susceptibility to channel impairments. The engineer should then select the technique that offers the best trade-off between these factors, ensuring that the chosen method is robust, efficient, and compliant with any relevant industry standards or regulations. This iterative process of analysis, evaluation, and selection, grounded in sound engineering principles and ethical considerations, is crucial for successful project outcomes. Question 2. Assessment of the most appropriate method for determining the required capacitance to improve the power factor of an inductive load operating under sinusoidal steady-state conditions, considering efficiency and regulatory compliance. Option A. Determine the capacitance solely based on the apparent power of the load, ignoring the phase angle. Option B. Calculate the capacitance based only on the real power of the load, disregarding the reactive power component. Option C. Estimate the capacitance based on general industry guidelines for similar inductive loads without specific calculations. Option D. Calculate the initial reactive power demand and the desired reactive power at the target power factor, then determine the capacitance needed to supply the difference. The correct answer is D. Calculate the initial reactive power demand and the desired reactive power at the target power factor, then determine the capacitance needed to supply the difference. Explanation. This scenario presents a professional challenge in ensuring the accurate and safe application of sinusoidal steady-state analysis in a practical electrical system design, specifically concerning power factor correction. The challenge lies in selecting the appropriate method for determining the required capacitance to improve the power factor, which directly impacts system efficiency, voltage regulation, and compliance with utility regulations. A deep understanding of the underlying principles of sinusoidal steady-state analysis is crucial to avoid oversizing or undersizing the correction equipment, which can lead to financial waste, operational issues, or even system instability. Correct approach involves utilizing the Faser representation of voltage and current in conjunction with the concept of apparent power S, real power P, and reactive power Q. By calculating the initial reactive power demand and the desired reactive power at the target power factor, the required reactive power compensation can be determined. This compensation is then translated into the necessary capacitance value using the relationship between reactive power, voltage, and capacitance in AC circuits. This method represents best professional practice because it is grounded in fundamental electrical engineering principles and directly addresses the objective of power factor correction within the context of sinusoidal steady-state conditions. It ensures that the chosen capacitance value is precisely what is needed to achieve the desired power factor, thereby optimizing system performance and adhering to established engineering standards. An incorrect approach would be to solely rely on the apparent power of the load without considering the phase difference between voltage and current. Apparent power alone does not provide information about the reactive power component, which is what needs to be compensated. This failure to account for the phase angle leads to an inaccurate calculation of the required capacitance, potentially resulting in overcorrection or undercorrection. This is a regulatory and ethical failure as it deviates from sound engineering principles, leading to an inefficient and potentially non-compliant system design. Another incorrect approach would be to estimate the required capacitance based on empirical rules of thumb without performing the necessary calculations. While rules of thumb can sometimes provide a starting point, they are not a substitute for rigorous analysis, especially when precise performance and compliance are required. Relying on estimations without proper calculation can lead to significant deviations from the optimal solution, potentially causing issues such as voltage fluctuations or harmonic resonance, which are undesirable and can violate system design standards. This represents a failure to exercise due diligence and professional responsibility. A third incorrect approach would be to focus only on the real power of the load and ignore the reactive power component entirely. Real power is the useful power delivered to the load, while reactive power is necessary for establishing magnetic fields in inductive components. Ignoring reactive power means ignoring the primary cause of a low power factor and the need for correction. This leads to an incomplete analysis and an incorrect determination of the required capacitance, failing to achieve the desired power factor improvement and potentially violating utility power factor clauses. The professional reasoning process for similar situations should involve a systematic approach. 1. Clearly define the objective. In this case, it is to improve the power factor to a specified value. 2. Identify the relevant system parameters. This includes voltage, current, real power, and the initial power factor. 3. Apply fundamental principles. Utilize sinusoidal steady-state analysis, including Faser diagrams and power triangle concepts. 4. Perform necessary calculations. Determine the initial reactive power, the target reactive power, and the required reactive power compensation. 5. Select appropriate components. Calculate the capacitance value needed for compensation. 6. Verify the solution. Ensure the chosen capacitance value will achieve the desired power factor without causing adverse effects. 7. Document the analysis. Maintain clear records of calculations and design decisions for review and future reference. Question 3. Comparative studies suggest that when designing electrical systems incorporating energy storage elements like capacitors and inductors for applications relevant to the fundamentals of engineering fee, electrical and computer exams jurisdiction, United States, which of the following approaches best ensures regulatory compliance and professional responsibility? Option A. Prioritizing adherence to the National Electrical Code, NEC, and relevant IEE standards for energy storage systems, ensuring all design choices are validated against these established safety and performance benchmarks. Option B. Implementing energy storage solutions based on anecdotal evidence from online forums and informal discussions among engineers, without consulting official codes or standards. Option C. Relying exclusively on the technical specifications and performance claims provided in manufacturer datasheets for the chosen capacitor and inductor components, assuming they meet all necessary safety requirements. Option D. Selecting energy storage components based primarily on the lowest available purchase price, even if it means deviating from standard safety guidelines, or using components not explicitly certified for the intended application. The correct answer is A. Prioritizing adherence to the National Electrical Code, NEC, and relevant IEE standards for energy storage systems, ensuring all design choices are validated against these established safety and performance benchmarks. Explanation. This scenario presents a professional challenge in ensuring the safe and compliant integration of energy storage components within electrical systems, particularly when dealing with novel or less common applications. The challenge lies in navigating the regulatory landscape to ensure that the chosen energy storage method not only meets performance requirements, but also adheres to established safety standards and guidelines relevant to the fundamentals of engineering. Fee. Electrical and computer exams jurisdiction, which is the United States. Professionals must exercise careful judgment to avoid potential hazards and ensure system reliability. The correct approach represents best professional practice because it prioritizes adherence to established national standards and codes that govern electrical safety and energy storage systems. Specifically, it aligns with the principles and requirements set forth by organizations like the National Electrical Code, NEC, and relevant IEE standards, which are foundational for electrical engineering practice in the U.S. These standards are developed through rigorous consensus processes and are designed to protect life and property. By consulting these authoritative sources, engineers ensure that their design choices are validated, tested, and recognized for their safety and efficacy, thereby fulfilling their ethical and professional obligations. An incorrect approach that relies solely on manufacturer datasheets without independent verification or cross-referencing with established codes is professionally unacceptable. Manufacturer datasheets, while informative, are not regulatory documents and may not encompass all safety considerations or interoperability requirements mandated by national standards. Failure to consult the NEC or equivalent U.S. electrical codes represents a significant regulatory failure, as these codes are legally binding in most jurisdictions. This oversight could lead to designs that violate safety regulations, posing risks of fire, electrical shock, or equipment damage, and could result in project delays, fines, or legal liabilities. Another incorrect approach that involves prioritizing cost savings over compliance with safety standards is a severe ethical and regulatory failure. The FE exam emphasizes the engineer's responsibility to public safety. Disregarding established safety protocols for financial gain directly contravenes this fundamental ethical principle and the legal requirements of electrical codes. This approach demonstrates a lack of professional integrity and a disregard for the potential consequences of unsafe designs. The professional reasoning process for similar situation should involve a systematic approach. First, clearly define the system requirements and the intended application of energy storage. Second, identify all applicable U.S. federal, state, and local regulations, as well as relevant industry standards, e.g., NEC, IEEE. Third, thoroughly research and evaluate potential energy storage solutions, always cross-referencing their specifications and proposed integration methods against the identified regulatory and standard requirements. Fourth, consult with experienced professionals or regulatory bodies if any ambiguities arise. Finally, document all design decisions and their justifications, demonstrating a clear path of due diligence and compliance. Question 4. Stakeholder feedback indicates a desire to minimize the overall cost of a new electrical installation by reducing the apparent power drawn from the utility. As the lead electrical engineer, you are tasked with developing the design strategy, which approach best balances cost considerations with efficient power utilization and regulatory compliance. Option A. Focus solely on reducing the real power consumption of the equipment, assuming this will directly minimize apparent power and associated costs. Option B. Design the system to achieve a power factor as close to unity as practically achievable, thereby minimizing reactive power and ensuring efficient use of apparent power. Option C. Design the system to minimize apparent power by increasing reactive power compensation, without explicit consideration of the resulting power factor. Option D. Prioritize selecting the lowest cost equipment, even if it results in a significantly lagging or leading power factor, as this will inherently reduce apparent power. The correct answer is B. Design the system to achieve a power factor as close to unity as practically achievable, thereby minimizing reactive power and ensuring efficient use of apparent power. Explanation. Scenario analysis. This scenario presents a common challenge in electrical engineering, where different stakeholders have varying priorities regarding power quality and system efficiency. The project managers focus on immediate cost savings through minimizing apparent power, while seemingly straightforward, overlooks critical aspects of system performance and regulatory compliance. The electrical engineer must balance these competing demands, ensuring the final design is not only cost-effective, but also meets technical standards and avoids potential penalties or operational issues related to power factor. This requires a deep understanding of AC power principles beyond simple magnitude calculations. Correct approach analysis. The correct approach prioritizes a balanced consideration of real power, reactive power, and apparent power, with a focus on achieving an acceptable power factor. This aligns with best professional practices and regulatory expectations for efficient power utilization. By aiming for a power factor close to unity, the system minimizes reactive power flow, which reduces losses in transmission and distribution lines, lowers voltage drop, and allows for more efficient use of existing infrastructure. This approach directly addresses the underlying technical reasons for power factor correction requirements often stipulated in utility tariffs and industry standards, preventing potential penalties and ensuring reliable operation. It demonstrates a commitment to engineering best practices by optimizing system performance and resource utilization. Incorrect approaches analysis. Focusing solely on minimizing apparent power without considering the power factor is an incomplete and potentially detrimental approach. Apparent power is the vector sum of real and reactive power. Reducing apparent power by increasing reactive power, e.g., through inductive loads without compensation, would lead to a poor power factor, increased current for the same real power, higher I2R losses, and potential voltage regulation issues. This would likely violate utility regulations concerning power factor limits, leading to financial penalties and operational inefficiencies. Another incorrect approach would be to ignore reactive power entirely and only focus on real power. Real power is the useful work done. Reactive power is essential for establishing magnetic fields in inductive components, like motors, and electric fields in capacitive components. Neglecting its impact means failing to account for the total current drawn from the source, which is directly related to apparent power and system capacity. This oversight can lead to overloading of transformers and conductors, and again, non-compliance with power factor regulations. Finally, prioritizing only the lowest initial equipment cost without considering the long-term implications of power factor and efficiency is a short-sighted approach. While initial capital expenditure is a factor, the operational costs associated with inefficient power usage, higher energy bills due to poor power factor penalties, increased losses, can significantly outweigh initial savings. This approach fails to consider the total cost of ownership and the broader impact on system reliability and sustainability, which are key ethical and professional considerations. Professional reasoning. Professionals should employ a decision-making framework that begins with a thorough understanding of project requirements, including stakeholder expectations and regulatory mandates. This involves identifying all relevant technical parameters, such as real, reactive, and apparent power, and their interrelationship's power factor. The next step is to evaluate potential design choices against these parameters, considering not only immediate cost, but also long-term operational efficiency, reliability, and compliance. A critical part of this process is consulting relevant codes, standards, and utility guidelines to ensure the design meets all legal and ethical obligations. When faced with conflicting priorities, professionals must advocate for solutions that uphold engineering integrity and best practices, even if it requires educating stakeholders on the technical and economic consequences of suboptimal choices. Question 5. To address the challenge of analyzing a complex linear electrical network's behavior when connected to a variable load, an engineer needs to select the most effective simplification technique. Considering the typical applications and conceptual advantages of circuit simplification theorems, which of the following best describes the preferred approach for understanding the voltage and current delivered to the load? Option A. Employ the Venon's theorem to represent the network as a single voltage source in series with an equivalent resistance, which simplifies the analysis of how different load impedances affect the circuit's output. Option B. Utilize a superposition theorem to analyze the network's response to each independent source individually, and then sum the results, regardless of the load's nature. Option C. Apply Kirchhoff's voltage and current laws to the entire network without any simplification, as this is the most fundamental and universally applicable method. Option D. Directly analyze the entire complex network for each potential load variation to ensure absolute accuracy, bypassing any simplification theorems. The correct answer is A. Employ the Venon's theorem to represent the network as a single voltage source in series with an equivalent resistance, which simplifies the analysis of how different load impedances affect the circuit's output. Explanation. Scenario analysis. This scenario presents a professional challenge because it requires an engineer to select the most appropriate method for simplifying a complex electrical circuit for analysis, specifically when dealing with a load that might be replaced or varied. The challenge lies in understanding the fundamental principles behind the Venon's and Norton's theorems and their practical implications in circuit design and troubleshooting, ensuring that the chosen method leads to accurate and efficient analysis without unnecessary complexity. Adherence to the fundamentals of engineering, FE, electrical and computer exam scope, which focuses on foundational engineering principles within the U.S. regulatory framework, is paramount. Correct approach analysis. The correct approach involves recognizing that the Venon's theorem is best suited when the goal is to analyze the behavior of a circuit with respect to a specific load, especially when that load is expected to change or be replaced. The Venon's theorem simplifies any linear electrical network into an equivalent circuit consisting of a single voltage source, VTH, in series with a single resistor, RTH. This simplification is invaluable for predicting how different load impedances will affect the circuit's output voltage and current without reanalyzing the entire original network each time. This aligns with best professional practice by promoting efficiency and accuracy in design and troubleshooting, which are core tenets of professional engineering conduct as implicitly guided by standards of practice within the U.S. engineering profession. The FE exam's emphasis on these foundational theorems underscores their importance in practical electrical engineering problem solving. Incorrect approaches analysis. One incorrect approach would be to solely rely on Norton's theorem without considering the specific application. While Norton's theorem, an equivalent current source in parallel with a resistor, is mathematically equivalent to the Venon's theorem, the Venon's is often more intuitive and directly applicable when voltage across a load is the primary concern, or when dealing with series combinations of components. Choosing Norton's theorem when the Venon's offers a more direct and conceptually simpler path to understanding load behavior could be considered inefficient, though not necessarily a regulatory failure in itself. Another incorrect approach would be to attempt to analyze the full complexity of the original circuit without any simplification. This is professionally unacceptable because it is time-consuming, prone to errors, and does not demonstrate an understanding of fundamental circuit simplification techniques that are expected of a licensed engineer. Such an approach would violate the principle of providing competent and efficient engineering services, potentially leading to delays and increased costs, which indirectly relates to the professional responsibility to act in the public interest by delivering reliable engineering solutions. A third incorrect approach would be to apply a theorem that is not applicable to linear circuits, such as attempting to use the Venon's or Norton's theorems on a circuit containing nonlinear components without proper linearization techniques. This would lead to inaccurate results and is a failure of fundamental engineering judgment, potentially resulting in faulty designs or analyses that could compromise safety or performance, a direct contravention of professional ethical obligations. Professional reasoning. Professionals should approach circuit simplification problems by first identifying the objective of the analysis. If the focus is on the behavior of a specific load, especially if that load is variable, then the Venon's or Norton's theorems are prime candidates. The decision between the Venon's and Norton's often comes down to which equivalent circuit provides a more straightforward analysis for the subsequent steps. If the problem requires understanding voltage drops or series circuit behavior, the Venon's is often preferred. If current division or parallel circuit behavior is more relevant, Norton's might be more suitable. The engineer must always verify that the circuit being analyzed is linear, as these theorems are derived for linear circuit elements. If the circuit is nonlinear, appropriate linearization techniques or alternative analysis methods must be employed. The FE exam tests the ability to select and apply these fundamental tools correctly, ensuring that engineers can efficiently and accurately solve practical problems. Question 6. The assessment process reveals that an electrical engineer is tasked with analyzing a complex circuit containing both voltage and current sources. The engineer needs to determine the voltage at a specific node within the circuit. Considering the principles of nodal and mesh analysis, which of the following represents the most conceptually sound and efficient approach for this engineer to adopt? Option A. Select nodal analysis, systematically identifying all independent nodes and applying Kirchhoff's current law at each to solve for the unknown node voltages. Option B. Apply both nodal and mesh analysis simultaneously to cross-verify results, even if one method is clearly more complex for the given circuit. Option C. Select mesh analysis, systematically identifying all independent meshes and applying Kirchhoff's voltage law around each, then deriving the node voltage from the mesh currents. Option D. Rely on a qualitative understanding of circuit behavior based on the types of sources present, without formally applying either nodal or mesh analysis. The correct answer is A. Select nodal analysis, systematically identifying all independent nodes and applying Kirchhoff's current law at each to solve for the unknown node voltages. Explanation. Scenario analysis. This scenario presents a common challenge in electrical engineering design, where a complex circuit requires analysis to ensure proper operation and safety. The challenge lies in selecting the most efficient and conceptually sound method for analyzing the circuit's behavior, specifically focusing on nodal and mesh analysis. Misapplication of these techniques can lead to design flaws, incorrect performance predictions, and potential safety hazards, all of which have significant professional and regulatory implications. The engineer must demonstrate a thorough understanding of the underlying principles and the practical application of these analysis methods. Correct approach analysis. The correct approach involves selecting the analysis method that best suits the circuit's topology and the specific parameters being investigated, prioritizing conceptual clarity and efficiency. For nodal analysis, this means identifying the number of independent nodes and applying Kirchhoff's current law, KCL, at each. For mesh analysis, it involves identifying the number of independent meshes and applying Kirchhoff's voltage law, KVL, around each. The choice between nodal and mesh analysis often depends on whether the circuit has more voltage sources, favoring mesh analysis, or current sources, favoring nodal analysis, or more nodes than meshes, or vice versa. This systematic application ensures accurate determination of unknown voltages or currents, which is fundamental to verifying circuit performance against design specifications and relevant safety standards, such as those outlined by the National Council of Examiners for Engineering and Surveying (NCs). For the fundamentals of engineering, FE exam, adhering to these established analytical methods represents best professional practice by ensuring a rigorous and verifiable design process. Incorrect approaches analysis. One incorrect approach would be to arbitrarily choose an analysis method without considering the circuit's structure or the desired outcome. For example, attempting mesh analysis on a circuit dominated by current sources without recognizing that nodal analysis would be significantly simpler and less prone to error represents a failure in analytical judgment. This can lead to unnecessary complexity, increased probability of calculation errors, even if calculations are not the focus of the question. The underlying process is, and a less efficient design process. Ethically, this could be seen as a failure to exercise due diligence in applying engineering principles. Another incorrect approach is to rely solely on intuition or past experience with similar circuits without a systematic application of nodal or mesh analysis principles. While experience is valuable, it should complement, not replace, fundamental analytical techniques. Failing to apply KCL or KVL correctly, or misidentifying the number of independent nodes or meshes, directly violates the core tenets of these analysis methods. This can result in incorrect circuit analysis, leading to designs that do not meet performance requirements or, more critically, fail to comply with safety regulations, potentially endangering users or equipment. This represents a failure to uphold professional standards of competence and accuracy. Professional reasoning. Professionals should approach circuit analysis by first examining the circuit topology. They should then identify the number of nodes and meshes and consider the types of sources present. The decision between nodal and mesh analysis should be based on which method will yield the most straightforward and efficient solution for the specific problem at hand, minimizing the number of equations and the potential for error. This systematic evaluation ensures that the chosen method is not only technically sound, but also practically efficient, aligning with professional obligations to deliver reliable and safe engineering solutions. Question 7. The audit findings indicate a potential discrepancy in the combinational logic of a safety-critical control system. The identified issue suggests that under specific, albeit rare, input conditions, the circuit may not produce the intended output, potentially compromising system safety. The engineering team is under pressure to resolve this quickly before the next system deployment. Which of the following approaches best addresses this situation while adhering to professional engineering standards and regulatory expectations for safety-critical systems? Option A. Immediately redesign the entire combinational logic block from scratch without a detailed analysis of the specific discrepancy, as a precautionary measure. Option B. Implement a minor modification to the circuit based on the audit team's suggestion, assuming it will resolve the issue, and proceed with the deployment to meet the deadline. Option C. Document the finding but defer any corrective actions until after the current deployment cycle, citing resource constraints and the low probability of the specific input conditions occurring. Option D. Conduct a thorough root cause analysis to understand the exact nature of the discrepancy, develop a corrected design, and implement comprehensive simulation and hardware testing to validate the fix before deployment. The correct answer is D. Conduct a thorough root cause analysis to understand the exact nature of the discrepancy, develop a corrected design, and implement comprehensive simulation and hardware testing to validate the fix before deployment. Explanation. Scenario analysis. The scenario presents a challenge where a critical combinational circuit design, intended for a safety-related system, has been implemented with a potential flaw identified during an audit. The professional challenge lies in balancing the urgency of addressing the potential safety issue with the need for rigorous verification and adherence to established design and testing protocols. Rushing a fix without proper validation could introduce new, unforeseen risks, while delaying a necessary correction could expose the system to the identified hazard. The engineer must navigate this by prioritizing safety, while ensuring the integrity and reliability of the design through systematic processes. Correct approach analysis. The correct approach involves a thorough root cause analysis of the identified discrepancy in the combinational circuit. This means meticulously reviewing the original design specifications, the implemented logic, and the test cases used for verification. The goal is to pinpoint the exact reason for the deviation and its potential impact on system functionality and safety. Once the root cause is understood, a revised design or correction should be developed and subjected to comprehensive simulation and hardware testing. This iterative process of design, verification, and validation, guided by established engineering standards and best practices for safety-critical systems, ensures that the fix is effective, does not introduce new issues, and meets all performance and safety requirements. This aligns with the fundamental ethical obligation of engineers to protect public safety and welfare, as well as regulatory requirements for robust design and verification in critical applications. Incorrect approach is analysis. Implementing a quick patch without understanding the root cause is a significant regulatory and ethical failure. It bypasses the essential verification steps, risking the introduction of new, potentially more severe, faults. This approach disregards the principle of due diligence and could lead to a system that appears fixed but remains unsafe, violating the engineer's duty to public safety. Ignoring the audit finding due to time constraints or perceived minor impact is another critical failure. It demonstrates a disregard for established quality assurance processes and the potential for even minor design flaws to escalate into major safety hazards in a critical system. This negligence can lead to regulatory noncompliance and severe ethical breaches, as it prioritizes expediency over safety. Modifying the circuit based on assumptions without any form of verification or testing is fundamentally unsound engineering practice. It relies on guesswork rather than evidence-based design and validation. This approach fails to meet the standards of professional engineering practice and exposes the system to unacceptable risks, violating the engineer's responsibility to ensure the reliability and safety of their work. Professional reasoning. In situations involving potential safety hazards in critical systems, engineers must adopt a systematic and risk-averse approach. The decision-making process should prioritize safety above all else. This involves 1. Acknowledging and thoroughly investigating any reported issues, such as audit findings. 2. Conducting a comprehensive root cause analysis to understand the problem fully. 3. Developing and rigorously testing potential solutions, ensuring they are validated against specifications and safety requirements. 4. Documenting all steps of the process, including design changes, testing results, and risk assessments. 5. Seeking peer review or expert consultation when necessary. This structured approach ensures that decisions are informed, defensible, and ultimately lead to the safest and most reliable outcome, upholding professional integrity and regulatory compliance. Question 8. Quality control measures reveal that a newly designed communication system, intended for a critical infrastructure application, utilizes multiplexers and demultiplexers for data routing. The design team has proposed using off-the-shelf components that meet the basic functional requirements, but lack detailed specifications regarding their performance under electromagnetic interference (EMI) or their long-term reliability in high-temperature environments. Which of the following approaches best aligns with regulatory compliance and professional engineering best practices for this application? Option A. Prioritize components with comprehensive datasheets that include detailed specifications on noise immunity, temperature range, and failure rates, and ensure the control signals are robustly designed to prevent unintended data paths. Option B. Select the least expensive components that satisfy the fundamental bit width and speed requirements, assuming standard operating conditions. Option C. Utilize components with generic specifications, as long as they can be integrated into the existing circuit board layout. Option D. Implement the components with minimal verification of control signal integrity, relying on the assumption that the system will operate within nominal parameters. The correct answer is A. Prioritize components with comprehensive datasheets that include detailed specifications on noise immunity, temperature range, and failure rates, and ensure the control signals are robustly designed to prevent unintended data paths. Explanation. Scenario analysis. This scenario presents a professional challenge related to the implementation of digital logic components, specifically multiplexers and demultiplexers, within a system designed for a regulated industry. The challenge lies in ensuring that the chosen components and their configuration not only meet performance specifications, but also adhere to the stringent safety and reliability standards mandated by the governing regulatory framework for electrical and computer engineering in the United States, as implied by the FE Electrical and Computer Exams jurisdiction. Failure to comply can lead to system malfunction, data corruption, safety hazards, and significant legal and financial repercussions. The need for robust design and verification is paramount. Correct approach analysis. The correct approach involves selecting multiplexers and demultiplexers that are certified or qualified for use in safety-critical applications, if applicable, or, at a minimum, have well-documented specifications and proven reliability. This includes verifying that the chosen components meet the required bit width, propagation delay, and power consumption characteristics without exceeding operational limits. Furthermore, The design must ensure that the control signals for the multiplexer/demultiplexer are generated reliably and are immune to noise or interference that could lead to incorrect data routing. This aligns with general engineering best practices and the implicit requirement for due diligence in component selection and system design under U.S. regulatory oversight, which emphasizes safety, reliability, and adherence to established standards, e.g., IEEE standards, relevant industry-specific regulations. The focus is on preventing unintended data paths or signal loss, which are critical for system integrity. Incorrect approaches analysis, selecting components based solely on the lowest cost without verifying their suitability for the application's operational environment and reliability requirements, is a significant regulatory and ethical failure. This approach disregards the potential for component failure, which could compromise system functionality and safety, violating the principle of designing for reliability and the implicit duty to protect the public. Choosing components with generic specifications that do not explicitly address factors like signal integrity, noise immunity, or operating temperature ranges, especially if the system is intended for environments with potential for such issues, is another failure. This demonstrates a lack of thoroughness in the design process and an insufficient understanding of the operational context, potentially leading to unpredictable behavior and noncompliance with implicit performance standards. Implementing multiplexers and demultiplexers without a clear and verifiable strategy for handling control signal integrity and potential race conditions is also professionally unacceptable. This oversight can lead to data being routed to the wrong destination or data loss, directly impacting system accuracy and reliability. Such an approach fails to meet the fundamental engineering responsibility of ensuring predictable and controlled system operation, which is a cornerstone of regulatory compliance in engineering. Professional reasoning. Professionals should approach such design challenges by first understanding the specific regulatory requirements and industry standards applicable to the system's intended use. This involves identifying any safety-critical aspects and selecting components that meet or exceed the necessary reliability and performance benchmarks. A thorough review of component datasheets, manufacturer qualifications, and potential failure modes is essential. The design process should incorporate robust verification and validation steps, including simulation and, where appropriate, hardware testing, to ensure that the multiplexer and demultiplexer functions operate as intended under all expected operating conditions. This systematic approach, grounded in risk assessment and adherence to established engineering principles and regulations, ensures the integrity, safety, and compliance of the final product. Question 9. Consider a scenario where an electrical engineer in the United States is designing a control system for a critical medical device that monitors patient vital signs. The system relies on a series of logic gates to process sensor inputs and trigger alarms. The engineer must select the appropriate logic gates and or, not, NAND, nor, XOR, XNOR, for this safety-critical application. Which of the following selection criteria best aligns with U.S. regulatory frameworks and professional engineering ethics for such a system? Option A. Prioritizing logic gates that have a proven history of high reliability in safety-critical applications and meet stringent performance specifications outlined in relevant U.S. engineering standards. Option B. Selecting logic gates based on the lowest unit cost to ensure the overall affordability of the medical device. Option C. Opting for logic gates with the smallest physical footprint to maximize space within the device's enclosure. Option D. Choosing logic gates that are readily available from multiple suppliers, assuming all logic gates of a given type are functionally equivalent. The correct answer is A. Prioritizing logic gates that have a proven history of high reliability in safety-critical applications and meet stringent performance specifications outlined in relevant U.S. engineering standards. Explanation. This scenario presents a professional challenge because the engineer is tasked with selecting logic gates for a safety-critical system. In the United States, the design and implementation of such systems are governed by various standards and regulations, including those from the National Electrical Code, NEC, and potentially industry-specific standards like those from the Institute of Electrical and Electronics Engineers, IEEE, or specific governmental bodies depending on the application, e.g., FDA for medical devices, FAA for aviation. The primary professional responsibility is to ensure the system's reliability, safety, and compliance with all applicable codes and standards. A failure in a safety-critical system can have severe consequences, including injury, loss of life, or significant financial damage. Therefore, the engineer must exercise extreme diligence and adhere strictly to established engineering principles and regulatory requirements. The correct approach involves selecting logic gates based on their inherent reliability characteristics, fault tolerance, and suitability for the specific safety requirements of the system, as defined by relevant U.S. engineering standards and codes. This might involve choosing gates with proven track records in safety applications, considering redundancy, and ensuring that the chosen gates meet stringent performance and environmental specifications. This approach represents best professional practice because it prioritizes safety and reliability, aligning with the fundamental ethical obligations of an engineer to protect public welfare. Adherence to established U.S. engineering codes and standards ensures that the design is not only functional, but also meets the legally mandated safety benchmarks. An incorrect approach would be to select logic gates based solely on cost or availability, without a thorough evaluation of their suitability for a safety-critical application. This is professionally unacceptable because it disregards the potential for catastrophic failure and violates the engineer's duty to ensure public safety. Such a decision could lead to non-compliance with U.S. electrical codes and safety regulations, potentially resulting in legal repercussions, project failure, and severe damage to the engineer's professional reputation. Another incorrect approach would be to assume that standard commercial-grade logic gates are sufficient, without verifying their specifications against the stringent requirements of a safety-critical system. This demonstrates a lack of due diligence and a failure to understand the elevated risks associated with such applications, potentially leading to system malfunction and safety hazards. The professional decision-making process in such situations should involve a systematic risk assessment, a thorough review of applicable U.S. codes and standards, consultation with subject matter experts, and rigorous testing and validation of chosen components. Engineers must always prioritize safety and compliance, even if it means incurring higher costs or longer development times. Question 10. The investigation demonstrates that a digital control system's logic circuit, initially defined by a complex Boolean expression, needs to be simplified for implementation on a programmable logic device. The goal is to achieve the most minimal logic while ensuring it precisely replicates the original functionality across all possible input combinations. The design team is considering several methods to achieve this simplification. Option A. Directly implementing the original complex Boolean expression without any simplification, arguing that modern programmable logic devices can handle the complexity. Option B. Applying a simplified version of Boolean algebra where certain terms are assumed to be negligible based on typical operating conditions, without formal proof of their irrelevance. Option C. Visually inspecting the truth table and intuitively identifying terms that appear less significant or less likely to occur, then removing them from the expression. Option D. Employing Carnot maps or systematic Boolean algebra to derive the minimal sum of products, SOP, or product of sums POS, form, rigorously verifying the grouping of adjacent 1 or 0 to cover all necessary minterms or maxterms. The correct answer is D. Employing Carnot maps or systematic Boolean algebra to derive the minimal sum of products SOP, or product of sums POS form, rigorously verifying the grouping of adjacent 1 or 0 to cover all necessary minterms or maxterms. Explanation. This scenario is professionally challenging because it involves a critical design decision with potential implications for system reliability and safety, even if not directly tied to immediate financial loss. The engineer must balance the desire for a simplified design with the need to ensure the logic accurately reflects the intended functionality. The core of the challenge lies in understanding the nuances of Boolean algebra and Carnot maps not just as mathematical tools, but as methods for representing and verifying logical operations in a real-world system. The correct approach represents best professional practice because it prioritizes a thorough and verifiable method for logic simplification. Using Carnot maps or systematic Boolean algebra to derive the simplest sum of products, SOP, or product of sums POS, form ensures that the resulting logic circuit is minimal, while still being functionally equivalent to the original, more complex expression. This adherence to established simplification techniques, as implicitly expected by the fundamentals of engineering. Fee. Electrical and computer exams focus on foundational engineering principles, demonstrates a commitment to robust design and the avoidance of unnecessary complexity, which can lead to errors in implementation or troubleshooting. The FE exam scope implies a need for engineers to apply these fundamental tools correctly and efficiently. An incorrect approach that relies on visual inspection or intuition without a systematic method fails to provide the necessary rigor. This can lead to errors where a simplification appears correct, but is not functionally equivalent, potentially causing the system to behave unexpectedly under certain input conditions. This lack of systematic verification is a failure in professional due diligence, as it bypasses established engineering methodologies designed to ensure correctness. It also fails to meet the implicit standard of competence expected by the FE exam, which assesses the ability to apply these tools accurately. Another incorrect approach might involve oversimplification, where essential terms are dropped based on assumptions about input signal probabilities or operating conditions that are not explicitly defined or guaranteed. This is ethically problematic because it introduces unverified assumptions into the design, potentially compromising the system's integrity if those assumptions are violated. It demonstrates a lack of understanding of the absolute nature of logical operations in a digital system, where every input combination must be accounted for, unless explicitly excluded by design specifications. This approach also fails to align with the rigorous, all-encompassing nature of the engineering principles tested in the FE exam. The professional reasoning process for similar situations should involve 1. Clearly defining the functional requirements of the logic circuit. 2. Selecting an appropriate and systematic method for simplification, e.g., Carnot maps, Boolean algebra. 3. Executing the simplification process meticulously, verifying each step. 4. If necessary, using a truth table to confirm the functional equivalence of the original and simplified logic. 5. Documenting the simplification process and the final logic design. This structured approach ensures accuracy, traceability, and adherence to engineering best practices, aligning with the foundational knowledge assessed by the FE exam. Question 11. Upon reviewing the timing specifications for a critical flip-flop in a new embedded system design, an engineer notices that the datasheet clearly defines setup time and hold time parameters. The engineer is considering whether to prioritize optimizing the clock frequency for maximum system throughput, or to ensure that the data inputs to the flip-flop are stable for at least the specified setup and hold times before and after the clock edge, respectively. What is the most critical consideration for ensuring the reliable operation of this flip-flop? Option A. Assuming that standard clock frequencies will inherently satisfy all flip-flop timing requirements. Option B. Focusing solely on the propagation delay of the flip-flop to determine its switching speed. Option C. Maximizing the clock frequency to achieve the highest possible system operating speed. Option D. Ensuring that the data inputs meet the specified setup and hold time requirements relative to the clock edge. The correct answer is D. Ensuring that the data inputs meet the specified setup and hold time requirements relative to the clock edge. Explanation. This scenario is professionally challenging because the successful and reliable operation of digital systems, particularly those involving sequential logic like microprocessors and state machines, hinges on the precise timing of data capture. Flip-flops, as fundamental memory elements, are highly sensitive to setup and hold time violations. Failure to adhere to these timing parameters can lead to unpredictable system behavior, data corruption, and intermittent errors that are notoriously difficult to debug. The professional engineer must understand the underlying principles of flip-flop operation and the implications of violating its timing specifications to ensure system integrity and meet performance requirements. The correct approach represents best professional practice because it directly addresses the fundamental operational constraints of the flip-flop. Understanding setup time, the minimum time data must be stable before the clock edge, and hold time, the minimum time data must remain stable after the clock edge, is crucial for designing synchronous digital circuits. By ensuring that the data inputs to the flip-flop meet these timing requirements, the engineer guarantees that the flip-flop will reliably capture the intended data state on the active clock edge. This adherence to datasheet specifications is a core tenet of digital design, and is implicitly required by general engineering principles of designing for reliability and functionality, as outlined in professional engineering codes of conduct that emphasize competence and due care. An incorrect approach that focuses solely on the clock frequency, without considering setup and hold times, is professionally unacceptable. This failure represents a disregard for the fundamental operational parameters of the flip-flop. The clock frequency dictates how often the flip-flop attempts to capture data, but it does not guarantee that the data itself is stable for the required durations. This can lead to setup time violations if data propagation delays are too long relative to the clock period, or hold time violations if data changes too quickly after the clock edge. Such oversights can result in the flip-flop capturing incorrect data, leading to system malfunction and potential safety hazards if the system controls critical functions. This demonstrates a lack of due diligence and technical competence, violating professional ethical obligations to produce sound engineering designs. Another incorrect approach that prioritizes only the propagation delay of the flip-flop is also professionally flawed. While propagation delay is an important characteristic affecting the overall system speed, it is distinct from setup and hold times. Propagation delay describes how long it takes for the output to change after the clock edge, whereas setup and hold times concern the stability of the input data relative to the clock edge. Ignoring setup and hold times while focusing solely on propagation delay can lead to the same data capture errors as mentioned above. This demonstrates a superficial understanding of digital timing and a failure to apply comprehensive analysis, which is a breach of professional responsibility to ensure the design's robustness. The professional reasoning process for similar situations should involve a systematic analysis of all critical timing parameters specified in component datasheets. This includes not only clock frequency and propagation delay, but, crucially, setup and hold times. Engineers must perform timing analysis, often with the aid of electronic design automation (EDA) tools, to verify that all timing constraints are met across all operating conditions and process variations. When faced with potential timing issues, the engineer must investigate the root cause, which could involve optimizing circuit layout, adjusting clock speeds, or selecting components with more favorable timing characteristics. This methodical approach, grounded in a thorough understanding of device physics and timing principles, is essential for delivering reliable and high-performing digital systems. Question 12. Strategic planning requires a thorough understanding of electrical system behavior under various operating conditions. An electrical engineer is tasked with evaluating a three-phase distribution panel that is experiencing a noticeable imbalance in the current drawn by its connected loads. The engineer's primary objective is to ensure the system's safety, efficiency, and longevity, adhering strictly to U.S. regulatory frameworks and professional engineering ethics. Which of the following approaches best reflects sound professional practice in addressing this situation? Option A. Analyze the current distribution across each phase to identify the extent of the imbalance and investigate the specific loads contributing to it, then propose solutions to equalize the loads or mitigate the effects of the imbalance. Option B. Immediately replace the main feeder conductors supplying the panel with a larger gauge to accommodate the potential for increased current due to the imbalance. Option C. Focus solely on ensuring the overcurrent protection devices, circuit breakers or fuses, are adequately sized for the total connected load, without addressing the phase imbalance itself. Option D. Advise the client that as long as the system is not visibly failing, the current load imbalance is acceptable and does not require immediate attention. The correct answer is A. Analyze the current distribution across each phase to identify the extent of the imbalance and investigate the specific loads contributing to it, then propose solutions to equalize the loads or mitigate the effects of the imbalance. Explanation. This scenario presents a professional challenge because the engineer must ensure the safe and efficient operation of an electrical system under non-ideal conditions. The presence of unbalanced loads can lead to several issues, including overheating of conductors, reduced system efficiency, and potential damage to equipment. The engineer's judgment is critical in identifying the root cause and implementing appropriate mitigation strategies, adhering to established engineering standards and safety regulations. The correct approach represents best professional practice because it directly addresses the potential consequences of unbalanced loads by focusing on system analysis and load balancing. This aligns with the fundamental engineering principle of ensuring system integrity and reliability. Specifically, in the U.S. regulatory framework, adherence to the National Electrical Code, NEC, is paramount. The NEC provides guidelines for conductor sizing, overcurrent protection, and grounding, all of which are impacted by load imbalances. By analyzing the load distribution and considering methods to equalize the phases, the engineer is proactively preventing potential hazards and ensuring compliance with safety standards. This approach demonstrates a commitment to public safety and the responsible application of electrical engineering principles. An incorrect approach that involves simply increasing the size of the main feeder conductors without investigating the cause of the imbalance is professionally unacceptable. This is because it fails to address the underlying problem, which could be due to faulty equipment, improper wiring, or a fundamental design flaw. Such a solution is a costly and inefficient workaround that does not guarantee safety or optimal performance. Ethically, it represents a failure to exercise due diligence and a potential violation of professional engineering standards that require engineers to act with competence and integrity. From a regulatory standpoint, while larger conductors might meet a minimum safety requirement, they do not address the root cause of the imbalance, which could still lead to other issues like voltage distortion or premature equipment failure, potentially violating the spirit, if not the letter, of safety codes. Another incorrect approach, such as ignoring the imbalance because the system is currently functioning without obvious failure, is a significant regulatory and ethical lapse. This demonstrates a lack of foresight and a disregard for potential future problems. The NEC and other safety standards are designed to prevent failures, not just react to them. Ignoring an identified issue like load imbalance is a direct contravention of the engineer's responsibility to ensure a safe and reliable system. It also fails to uphold the ethical obligation to protect the public from harm. The professional decision-making process for similar situations should involve a systematic approach. 1. Identify and quantify the problem. Accurately measure the load on each phase to determine the degree of imbalance. 2. Analyze the root cause. Investigate why the loads are unbalanced. This might involve inspecting connected equipment, reviewing wiring diagrams, and understanding the operational characteristics of the loads. 3. Evaluate potential consequences. Understand how the imbalance is affecting or could affect the system, e.g., overheating, voltage issues, equipment stress. 4. Develop and evaluate solutions. Consider various mitigation strategies, such as redistributing loads, adding balancing reactors, or recommending changes to the connected equipment. 5. Select the most appropriate solution. Choose the solution that is technically sound, cost-effective, and compliant with all applicable regulations and codes, prioritizing safety and long-term reliability. 6. Document the process. Maintain thorough records of the analysis, chosen solution, and any implemented changes. Question 13. Examination of the data shows that a critical control system requires a digital element to reliably store a single bit of information and maintain that state until a specific clock edge triggers an update. The element must be synchronized with the system clock to ensure predictable operation. Which type of flip-flop is most fundamentally suited for this requirement? Option A. JK flip-flop configured as a T flip-flop. Option B. D flip-flop. Option C. T flip-flop. Option D. SR latch. The correct answer is B. D flip-flop. Explanation. This scenario presents a professional challenge because the selection of a flip-flop type for a critical control system component requires a thorough understanding of its operational characteristics and adherence to established design principles, which are implicitly governed by the standards expected in the Fundamentals of Engineering, FE, Electrical and Computer Exam. The challenge lies in ensuring the chosen flip-flop reliably implements the intended logic without introducing unintended behavior, which could compromise system integrity and safety. Careful judgment is required to balance performance, complexity, and adherence to fundamental digital logic design practices. The correct approach represents best professional practice because it prioritizes the fundamental behavior of the flip-flop that directly addresses the stated requirement of maintaining its state until a clock edge. A D flip-flop is designed to capture its input D at the active clock edge and hold that value until the next active clock edge. This inherent characteristic directly fulfills the need to store and maintain a single bit of information reliably, which is a core function in sequential logic design. This aligns with the principles of robust digital system design, emphasizing predictable and deterministic behavior, which is a cornerstone of engineering practice and implicitly expected in professional examinations. An incorrect approach that selects an SR latch without considering its potential for race conditions or invalid states when both S and R inputs are asserted simultaneously is professionally unacceptable. While an SR latch can hold a state, its behavior is not as strictly defined by a clock edge as a D flip-flop, making it less suitable for synchronous systems where precise timing is crucial. This failure to select a clock-synchronous element for a clock-dependent operation violates fundamental digital design principles and could lead to unpredictable system behavior, a direct contravention of the expectation for reliable engineering solutions. Another incorrect approach that chooses a JK flip-flop and configures it to operate as a T flip-flop by tying J and K inputs together, while functionally possible, introduces unnecessary complexity and potential for confusion in documentation and maintenance. The direct selection of a T flip-flop, if available and appropriate, would be a more straightforward and maintainable design choice. This approach, while not necessarily leading to immediate failure, demonstrates a lack of optimal design practice, which is implicitly assessed in professional engineering evaluations. It suggests a less efficient use of available components and a potential for misinterpretation by future engineers working on the system. Finally, an incorrect approach that selects a T flip-flop but fails to consider its toggle behavior when both inputs are asserted would be a significant failure. A T flip-flop's primary function is to toggle its output on each clock pulse when enabled. If the requirement is to simply hold a state, a T flip-flop is not the most direct or efficient choice, and misapplying its functionality would lead to incorrect system operation. This demonstrates a fundamental misunderstanding of the flip-flop's intended purpose and its application in digital circuits. The professional decision-making process for similar situations should involve 1. Clearly defining the functional requirement, e.g., state holding, toggling data transfer. 2. Identifying the available digital logic elements, latches and flip-flops, and their fundamental operating principles. 3. Evaluating each element's suitability against the defined requirement, considering factors like clock synchronization, state stability, and potential for unintended behavior. 4. Selecting the simplest, most reliable, and most appropriate component that meets the requirement, prioritizing clarity and maintainability in the design. 5. Verifying the chosen component's behavior through simulation or analysis to ensure it functions as intended within the larger system context. Question 14. Performance analysis shows a newly designed DC power supply circuit intended for a sensitive electronic device. The circuit includes a large electrolytic capacitor and a small inductor in its output filtering stage. During steady-state operation, what is the expected behavior of these components within the DC circuit? Option A. The capacitor will act as a short circuit and the inductor will act as an open circuit. Option B. The capacitor will act as an open circuit and the inductor will act as a short circuit. Option C. Both the capacitor and the inductor will act as open circuits. Option D. Both the capacitor and the inductor will act as short circuits. The correct answer is B. The capacitor will act as an open circuit and the inductor will act as a short circuit. Explanation. The scenario presents a common challenge in electrical engineering, ensuring the proper functioning and safety of circuits containing reactive components like capacitors and inductors under direct current DC conditions. The professional challenge lies in understanding the transient and steady-state behavior of these components, which can significantly impact circuit performance and potentially lead to equipment damage or safety hazards if not correctly analyzed. The requirement to adhere strictly to the fundamentals of engineering, electrical and computer exams specified regulatory framework, laws, and guidelines means that any analysis must be grounded in the principles tested by that exam, which typically focus on foundational engineering knowledge and ethical practice within the United States. The correct approach represents best professional practice because it demonstrates a thorough understanding of fundamental electrical principles as applied to DC circuits, specifically the behavior of capacitors and inductors. In a DC circuit, a capacitor acts as an open circuit once fully charged, and an inductor acts as a short circuit once the current has stabilized. Recognizing these steady-state conditions is crucial for predicting circuit behavior, designing appropriate protection mechanisms, and troubleshooting issues. This understanding aligns with the ethical obligation of an engineer to ensure the safety, reliability, and efficiency of electrical systems, as implicitly required by professional engineering standards and the FE exam scope. An incorrect approach that fails to account for the steady-state behavior of capacitors and inductors in a DC circuit represents a significant regulatory and ethical failure. For instance, assuming a capacitor continuously draws current in a steady-state DC circuit would lead to incorrect power calculations and potentially oversizing of power supplies, violating principles of efficient design. Similarly, assuming an inductor presents resistance in a steady-state DC circuit would lead to inaccurate voltage drop calculations and misinterpretations of circuit behavior. These failures stem from a lack of fundamental knowledge, which is a direct contravention of the engineer's responsibility to possess and apply the necessary competence for the tasks undertaken. Such oversights could lead to designs that are not only inefficient but also potentially unsafe, violating the paramount duty to protect public health, safety, and welfare. The professional decision-making process for similar situations should involve a systematic approach. 1. Identify the circuit type DC or AC and the components present. 2. Recall and apply the fundamental behavior of each component under the given circuit conditions, transient and steady state. 3. Analyze the circuit's behavior based on these fundamental principles. 4. Consider potential implications for performance, safety, and efficiency. 5. Consult relevant codes, standards, and best practices if uncertainty exists, ensuring alignment with the jurisdiction's regulatory framework. 6. Document the analysis and design decisions clearly and comprehensively. Question 15. Operational review demonstrates that a linear electrical circuit containing multiple independent voltage and current sources is exhibiting unexpected behavior under certain load conditions. To accurately predict the circuit's response and identify the contribution of each source to the overall output voltage at a specific node, which of the following analytical approaches is the most appropriate and theoretically sound for this linear circuit? Option A. Measure the output voltage with all sources active, and then attempt to estimate the contribution of each source based on their relative magnitudes without a formal analytical method. Option B. Analyze the circuit by considering the effect of each independent source one at a time, while deactivating all other independent sources, replacing voltage sources with short circuits and current sources with open circuits, and then algebraically summing the individual responses. Option C. Analyze the circuit by applying all sources simultaneously, and then dividing the total measured output by the number of sources to determine the average contribution of each. Option D. Assume the circuit's behavior is solely determined by the source with the largest apparent magnitude, and disregard the influence of other sources. The correct answer is B. Analyze the circuit by considering the effect of each independent source one at a time, while deactivating all other independent sources, replacing voltage sources with short circuits and current sources with open circuits, and then algebraically summing the individual responses. Explanation. Scenario analysis. This scenario presents a professional challenge in verifying the performance of a complex electrical circuit under varying operating conditions. The challenge lies in ensuring that the design meets its intended specifications without resorting to potentially time-consuming or disruptive full-system testing for every possible scenario. The engineer must apply theoretical principles to predict behavior and identify potential issues efficiently and accurately. This requires a solid understanding of circuit analysis techniques and their practical application in a design verification context. Correct approach analysis. The correct approach involves utilizing the superposition theorem to analyze the circuit's response to each independent source individually, and then summing these responses. This method is best professional practice because it simplifies the analysis of linear circuits with multiple independent sources. By breaking down the problem into smaller, manageable parts, it allows for a systematic evaluation of each source's contribution to the overall output. This aligns with professional engineering standards that emphasize methodical problem-solving and efficient verification processes. The theorem is a fundamental concept in electrical engineering, widely accepted and taught, and its application is a standard technique for analyzing linear circuits, thus adhering to established engineering principles and best practices. Incorrect approach is analysis. One incorrect approach is to assume that the circuit's behavior is simply the sum of its responses to each source applied simultaneously without deactivating other sources. This violates the core principle of the superposition theorem, which requires independent sources to be considered one at a time, while others are replaced by their internal impedances, voltage sources by short circuits, current sources by open circuits. This failure to correctly apply the theorem leads to an inaccurate prediction of circuit behavior, which is a fundamental error in technical analysis and can result in flawed design decisions. Another incorrect approach is to attempt to analyze the circuit by directly measuring the output with all sources active, and then trying to infer the contribution of each individual source without a systematic method. This is inefficient and prone to error, especially in complex circuits. It bypasses the established theoretical framework that provides a structured and verifiable method for understanding source interactions. This approach lacks the rigor expected in professional engineering and does not provide a reliable basis for design validation. A third incorrect approach is to only consider the most dominant source and ignore the contributions of other sources, even if they are significant. While in some practical scenarios, one source might have a much larger impact, the superposition theorem is designed to account for the cumulative effect of all sources in a linear system. Ignoring other sources, even if seemingly minor, can lead to an incomplete understanding of the circuit's behavior and potentially overlook critical performance issues or safety concerns. This demonstrates a lack of thoroughness and adherence to established analytical methods. Professional reasoning. Professionals should approach circuit analysis by first identifying the type of circuit, linear or non-linear, and the number and types of sources. For linear circuits with multiple independent sources, the superposition theorem is a powerful tool. The decision-making process involves 1. Understanding the theoretical underpinnings of the chosen analysis method. 2. Systematically applying the steps of the theorem, ensuring all conditions are met, e.g., deactivating appropriate sources. 3. Verifying the results through alternative methods or sanity checks where possible. 4. Recognizing the limitations of the theorem, e.g., it applies only to linear circuits and is used for calculating voltages and currents, not power directly. When faced with a complex circuit, the professional's judgment should be guided by established engineering principles and the need for accurate, verifiable results that ensure the safety and functionality of the design system. Question 16. Analysis of a situation where an electrical engineer, working on a critical embedded system for a medical device, discovers a subtle flaw in the design of a state machine within a sequential logic circuit. This flaw, if triggered under specific, albeit rare, operating conditions, could lead to an incorrect output that might compromise the device's functionality and potentially affect patient safety. The project is under a strict deadline for regulatory submission. The engineer is aware that addressing this flaw would require significant redesign and testing, potentially causing a delay. What is the most ethically and professionally responsible course of action for the engineer? Option A. Proceed with the project as scheduled, assuming the rare conditions for triggering the flaw are unlikely to occur in real-world usage, and address it in a future software update if it becomes a problem. Option B. Document the vulnerability, assess its potential impact on patient safety and device functionality, and formally report it to the project manager and relevant stakeholders with recommendations for mitigation. Option C. Discreetly implement a workaround for the flaw without formal documentation or consultation, hoping it resolves the issue without causing further delays or raising concerns. Option D. Ignore the flaw, as it only manifests under rare conditions, and the immediate priority is meeting the regulatory submission deadline for the life-saving device. Correct answer is B. Document the vulnerability, assess its potential impact on patient safety and device functionality, and formally report it to the project manager and relevant stakeholders with recommendations for mitigation. Explanation. Scenario analysis. This scenario presents a professional challenge rooted in the ethical obligation to maintain the integrity and security of engineered systems. The engineer is faced with a situation where a known vulnerability in a sequential logic circuit, which could lead to system malfunction or unauthorized access, has been identified. The challenge lies in balancing the immediate demands of a project deadline with the long-term responsibility of ensuring system safety and reliability. The pressure to deliver a functional product quickly can create a conflict with the imperative to address potential risks, even if they are not immediately apparent or have not yet caused a failure. This requires careful judgment to prioritize safety and security over expediency. Correct approach analysis. The correct approach, which involves documenting the vulnerability, assessing its potential impact, and recommending mitigation strategies to the project manager and relevant stakeholders, represents best professional practice. This aligns with fundamental engineering ethics and professional conduct standards, such as those promoted by the National Society of Professional Engineers, NSPE, in the United States, which emphasize the engineer's duty to hold paramount the safety, health, and welfare of the public. By formally documenting the issue, the engineer creates a record of their due diligence and fulfills their responsibility to inform decision-makers about potential risks. This proactive stance allows for informed decisions regarding resource allocation for remediation, risk acceptance, or further investigation, thereby upholding the engineer's commitment to ethical practice and responsible engineering. Incorrect approaches analysis. Ignoring the vulnerability and proceeding with the project without disclosure is a significant ethical and professional failure. This approach violates the duty to protect public safety and can lead to severe consequences if the vulnerability is exploited or causes system failure. It demonstrates a disregard for professional responsibility and could result in legal liability and damage to the engineer's reputation and the company's. Concealing the vulnerability to avoid delaying the project or causing concern is also professionally unacceptable. This act of omission is deceptive and undermines trust. It prevents stakeholders from making informed decisions about risk management and could lead to a more significant problem down the line, with potentially greater repercussions. This behavior contravenes the principles of honesty and transparency expected of licensed engineers. Proposing a quick, undocumented fix without thorough analysis or stakeholder consultation is also problematic. While seemingly proactive, this approach bypasses proper engineering processes. It risks introducing new, unforeseen issues, may not adequately address the root cause of the vulnerability, and lacks the necessary documentation for future reference or auditing. This can lead to a false sense of security and does not fulfill the engineer's obligation to provide robust and well-documented solutions. Professional reasoning. Professionals should approach such situations by following a structured decision-making process. First, identify and clearly define the problem or potential risk. Second, gather all relevant information, including the nature of the vulnerability, its potential impact, and any contributing factors. Third, consult relevant professional codes of ethics and organizational policies. Fourth, communicate the findings and potential risks clearly and objectively to appropriate stakeholders, such as project managers, supervisors, or ethics committees, providing well-reasoned recommendations. Fifth, document all actions taken and communications. This systematic approach ensures that decisions are based on sound engineering principles, ethical consideration, and a commitment to public welfare, rather than on expediency or personal convenience. Question 17. Risk assessment procedures indicate that a new industrial control system may experience fluctuations in load characteristics due to the intermittent operation of several motor-driven pumps. The system utilizes AC power. The lead electrical engineer is reviewing the design to ensure proper operation and safety under these varying conditions. Considering the principles of phasors and complex impedance, which of the following conceptual approaches best addresses the potential impact of these load fluctuations on the system's voltage regulation and protective device coordination? Option A. Evaluating how the varying reactive components of the motor loads, represented by the imaginary part of their complex impedance, will affect the overall system impedance and the phase relationship between voltage and current under different load levels. Option B. Focusing solely on the magnitude of the complex impedance of each component, without considering the phase angle, as it is the primary determinant of current flow. Option C. Performing detailed transient simulations to determine exact current and voltage values at every microsecond, without a conceptual understanding of how impedance variations influence these values. Option D. Assuming all motor loads can be treated as purely resistive elements with a constant resistance value, simplifying calculations for steady-state operation. The correct answer is A. Evaluating how the varying reactive components of the motor loads, represented by the imaginary part of their complex impedance, will affect the overall system impedance and the phase relationship between voltage and current under different load levels. Explanation. This scenario presents a professional challenge because it requires an engineer to interpret and apply fundamental electrical engineering principles, specifically phasor analysis and complex impedance, within the context of a real-world system design. The challenge lies in understanding how these concepts influence system behavior and safety, particularly when dealing with potential fault conditions or unexpected loads. The engineer must move beyond simple calculation to a conceptual understanding of how impedance variations affect current and voltage, which is critical for ensuring the system operates within safe and intended parameters. The correct approach represents best professional practice because it directly addresses the core of the problem by considering the impact of varying impedances on the overall system's behavior under different operating conditions. This aligns with the fundamental ethical and professional responsibility of an engineer to design safe, reliable, and efficient systems. By focusing on the qualitative and conceptual implications of complex impedance in FASR form, the engineer demonstrates an understanding of how these abstract mathematical tools translate into tangible system performance and potential risks. This proactive consideration of impedance's role in system dynamics is a hallmark of sound engineering judgment and adherence to professional standards that prioritize system integrity and safety. An incorrect approach that focuses solely on nominal impedance values without considering their dynamic nature or the implications of phase shifts would be professionally unacceptable. This failure stems from a superficial understanding of complex impedance, neglecting the fact that impedance is not always a constant value and that its reactive component, represented by the imaginary part of the complex number in FASR analysis, significantly influences current flow and power factor, especially under transient or non-ideal conditions. This oversight could lead to underestimation of fault currents, miscalculation of voltage drops, or improper selection of protective devices, all of which violate the engineer's duty to ensure system safety and reliability. Another incorrect approach might involve treating the system as purely resistive, ignoring the reactive components of impedance. This is a critical regulatory and ethical failure because it fundamentally misrepresents the behavior of AC circuits, which are inherently characterized by inductive and capacitive elements. Such an approach would lead to inaccurate predictions of system performance, potentially causing equipment damage or operational failures, and directly contravening the expectation that engineers apply accurate and complete engineering principles. A third incorrect approach could be to dismiss the importance of phase angles in FASR representation, focusing only on the magnitude of impedance. This is a significant professional failing, as the phase angle is crucial for understanding power factor, reactive power, and the timing of voltage and current waveforms. Neglecting this aspect can lead to inefficient power utilization, resonance issues, and incorrect assessment of system stability, all of which are unacceptable in professional engineering practice. A professional decision-making process for similar situations should involve a systematic evaluation of the system's components and their interactions. This includes identifying all potential operating states, including normal operation, startup, shutdown, and fault conditions. For each state, the engineer must consider how the complex impedance of each component contributes to the overall system impedance, and how this affects voltage, current, and power. The use of FASR analysis should be employed not just for calculation, but for conceptual understanding of phase relationships and their impact on system dynamics. This analytical framework ensures that potential issues are identified and mitigated proactively, upholding the engineer's commitment to safety, reliability, and ethical practice. Question 18. Operational review demonstrates that a three-phase industrial load is exhibiting signs of imbalance. An engineer is tasked with assessing the total real power being consumed by this load. Which of the following approaches would most accurately reflect the actual real power consumption of the system under these conditions? Option A. Multiply the apparent power of one phase by 3, assuming this provides a reasonable approximation of the total system apparent power. Option B. Average the currents of the three phases and use this average current with the system voltage to calculate the total real power. Option C. Calculate the total apparent power by summing the apparent powers of each phase and then assume a nominal power factor for the entire system to determine the total real power. Option D. Calculate the real power for each phase individually using its respective voltage, current, and power factor, and then sum these individual real powers to obtain the total real power. The correct answer is D. Calculate the real power for each phase individually using its respective voltage, current, and power factor, and then sum these individual real powers to obtain the total real power. Explanation. Scenario analysis. This scenario presents a professional challenge because it requires an engineer to interpret and apply fundamental principles of three-phase power systems in a practical operational context. The challenge lies in understanding the implications of unbalanced loads on system performance and safety, which can lead to inefficiencies, equipment damage, and potential hazards. Accurate assessment is crucial for maintaining system integrity and ensuring compliance with operational standards. Correct approach analysis. The correct approach involves recognizing that in a three-phase system, the total power is the sum of the power in each phase. When dealing with unbalanced loads, it is essential to calculate the power for each phase individually and then sum them to determine the total real power consumed by the system. This method aligns with the fundamental principles of electrical engineering and ensures an accurate representation of the system's power consumption, which is critical for load balancing, capacity planning, and fault detection. This approach upholds professional responsibility by ensuring accurate system analysis, which is implicitly required by general engineering practice standards that emphasize safety, efficiency, and reliability. Incorrect approaches analysis. One incorrect approach is to assume that the apparent power of one phase can be directly multiplied by 3 to represent the total system apparent power, even with unbalanced loads. This is a regulatory and ethical failure, because it leads to a significant underestimation of the total system load. Such an error could result in overloading downstream equipment, inadequate power supply, and potential safety hazards, violating the engineer's duty to ensure the safe and reliable operation of electrical systems. Another incorrect approach is to focus solely on the voltage and current of the system, without considering the phase angles between them for each individual phase. In a three-phase system, especially with unbalanced loads, the phase angles are critical for calculating the true power factor and real power. Ignoring these phase relationships leads to an inaccurate calculation of real power and can mask issues like excessive reactive power or harmonic distortion, which can degrade system performance and damage equipment. This constitutes a failure to apply fundamental engineering principles, potentially leading to unsafe conditions and non-compliance with operational efficiency expectations. A third incorrect approach is to simply average the currents across the three phases and then use this average to calculate the total power. This method fails to account for the individual power contributions of each phase, which can vary significantly in an unbalanced system. The resulting power calculation would be inaccurate, potentially leading to misjudgments about system capacity and load distribution. This is a professional failing as it demonstrates a lack of understanding of how power is distributed and consumed in a three-phase system, which is a core competency for electrical engineers. Professional reasoning. Professionals should approach such scenarios by first identifying the system configuration, three-phase, and the nature of the load, potentially unbalanced. They should then recall or consult relevant engineering principles and standards for three-phase power calculations. The decision-making process involves selecting the method that most accurately reflects the physical behavior of the system. In this case, calculating power per phase and summing is the most robust method. Professionals must prioritize accuracy and safety, ensuring their analysis supports reliable and efficient system operation, thereby adhering to their ethical obligations and professional standards. Question 19. Research into the design of a new power distribution substation reveals that a specific capacitor bank installation is susceptible to parallel resonance at frequency close to a known harmonic present in the local grid. The project manager, citing budget constraints, suggests omitting a proposed passive harmonic filter designed to mitigate this resonance, arguing that the system has operated without incident in similar, albeit less critical, applications. As the lead electrical engineer responsible for the substation's design integrity, what is the most ethically and professionally sound course of action? Option A. Proceed with omitting the harmonic filter, assuming that the harmonic present is unlikely to cause significant issues in this specific configuration, and that the project manager's experience in similar applications is sufficient guidance. Option B. Insist on the inclusion of the harmonic filter, providing a detailed technical justification that outlines the risks of parallel resonance, including potential overvoltages, equipment damage, and system instability, and explaining how the filter addresses these risks according to established electrical engineering principles. Option C. Agree to omit the harmonic filter to meet the project budget, documenting the project manager's request and the potential risks, but deferring the final decision to a higher authority without further technical input. Option D. Propose a less expensive, alternative component that might offer some degree of harmonic mitigation, even if its effectiveness in preventing parallel resonance is not fully guaranteed by theoretical analysis or empirical data. The correct answer is B. Insist on the inclusion of the harmonic filter, providing a detailed technical justification that outlines the risks of parallel resonance, including potential overvoltages, equipment damage, and system instability, and explaining how the filter addresses these risks according to established electrical engineering principles. Explanation: this scenario presents a professional challenge because it involves a conflict between immediate cost-saving pressures and the long-term integrity of a critical electrical system. The engineer is tasked with ensuring the system operates reliably and safely, which includes understanding and managing resonant conditions. The pressure to reduce costs by omitting a component that mitigates resonance, even if it appears to be functioning adequately under current, non-resonant conditions, introduces significant risk. The correct approach represents best professional practice because it prioritizes the safety and reliability of the electrical system, adhering to fundamental engineering principles, and implicitly, the ethical obligation to protect public welfare. By recommending the inclusion of the damping component, the engineer is acting proactively to prevent potential catastrophic failures, equipment damage, and operational disruptions that can arise from uncontrolled resonance. This aligns with the professional responsibility to design and implement systems that are robust and safe under a range of operating conditions, not just ideal ones. The Fundamentals of Engineering, FE Electrical and Computer Exam, emphasizes a strong understanding of core electrical principles, including resonance, and their practical implications for system design and safety. An incorrect approach that prioritizes immediate cost savings over system integrity is professionally unacceptable. This failure stems from a disregard for the potential consequences of resonance, which can lead to overcurrents, overvoltages, and mechanical stress, ultimately causing equipment failure. Such an approach violates the engineer's duty to uphold public safety and welfare, a cornerstone of professional engineering ethics, and implicitly, the standards expected in professional licensure and examinations like the FE. Omitting a necessary component based on a superficial assessment of current operating conditions, without a thorough analysis of potential resonant frequencies and their impact, demonstrates a lack of due diligence and a failure to apply sound engineering judgment. This could also be seen as a failure to adhere to industry best practices and standards for electrical system design, which are implicitly tested in the FE exam. Another incorrect approach, such as relying solely on anecdotal evidence or the opinion of non-engineering personnel regarding the necessity of the damping component, is also professionally flawed. Engineering decisions must be based on objective analysis, data, and established principles, not on subjective opinions or expediency. This approach undermines the engineer's professional authority and responsibility, potentially leading to decisions that compromise system performance and safety. It fails to acknowledge the scientific basis of resonance and the importance of engineering analysis in mitigating its effects. The professional decision-making process for similar situations should involve a systematic evaluation of the system's operating parameters, potential failure modes, and the impact of design choices on safety and reliability. This includes a thorough understanding of the theoretical underpinnings of phenomena like resonance, as tested in the FE exam. The engineer must then weigh the risks and benefits of different design options, considering both immediate and long-term consequences. When faced with pressure to compromise on safety or reliability for cost reasons, the engineer must clearly articulate the technical justifications for their recommendations, referencing relevant engineering principles and standards. If necessary, the engineer should escalate concerns through appropriate channels to ensure that decisions are made with a full understanding of the technical implications. Question 20. Stakeholder feedback indicates a strong preference for a rapid and cost-effective implementation of an energy storage solution for a new electrical system. The project manager is pushing for the immediate selection of a capacitor that meets the basic capacitance and voltage requirements, with minimal consideration for long-term performance characteristics or adherence to specific industry standards beyond the manufacturer's basic specifications. As the lead electrical engineer, how should you proceed to ensure both stakeholder satisfaction and professional integrity? Option A. Consult relevant industry standards, e.g., IEEE standards, and local electrical codes to identify capacitor types and specifications that meet safety, performance, and reliability requirements for the intended application, and then present compliant options to the stakeholder, explaining the rationale behind each. Option B. Rely solely on the capacitor manufacturer's datasheet to confirm that the chosen component meets the project's immediate technical needs, without further investigation into broader industry or regulatory compliance. Option C. Immediately select the least expensive capacitor that meets the basic capacitance and voltage requirements, as requested by the project manager, to expedite the project timeline. Option D. Inform the project manager that cost is not a primary concern, and propose the most technologically advanced and expensive capacitor solution available, regardless of the project's actual needs or budget. The correct answer is A. Consult relevant industry standards, e.g., IEEE standards, and local electrical codes to identify capacitor types and specifications that meet safety, performance, and reliability requirements for the intended application, and then present compliant options to the stakeholder, explaining the rationale behind each. Explanation. Scenario analysis. This scenario is professionally challenging because it requires an engineer to balance the immediate need for system functionality with long-term reliability and safety considerations, all within the context of evolving technological standards and regulatory expectations. The stakeholders' desire for a quick, cost-effective solution could lead to compromises that violate established engineering principles and potentially safety regulations, necessitating a firm, evidence-based response from the engineer. Correct approach analysis. The correct approach represents best professional practice because it prioritizes adherence to established engineering codes and standards, which are often codified into regulatory requirements for electrical systems. By consulting relevant IEEE standards and local electrical codes, e.g., National Electrical Code in the U.S., if that were the specified jurisdiction, the engineer ensures that the chosen energy storage solution meets minimum safety, performance, and interoperability requirements. This proactive stance prevents potential hazards, ensures system longevity, and aligns with the ethical obligation to protect public safety and welfare, as mandated by professional engineering licensing bodies and their codes of ethics. Incorrect approaches analysis. One incorrect approach involves immediately implementing the cheapest available capacitor without regard for its specifications or suitability for the application. This fails to meet regulatory requirements for component selection, which often mandate adherence to specific standards, e.g., UL certification for safety. Ethically, it violates the duty to perform services competently and to avoid actions that could endanger the public. Another incorrect approach is to rely solely on the manufacturer's datasheet without cross-referencing it with industry standards or considering the operating environment. While datasheets provide crucial information, they do not guarantee compliance with broader regulatory frameworks or best practices for system integration. This can lead to a system that, while meeting individual component specs, is not safe or reliable in its intended application, potentially violating regulations that require a holistic system design approach. A third incorrect approach is to dismiss the stakeholders' concerns about cost and immediately propose the most advanced and expensive solution without exploring viable, compliant alternatives. While prioritizing safety and reliability is paramount, engineers also have a professional responsibility to consider economic factors and provide cost-effective solutions where possible, without compromising safety or regulatory compliance. This approach could be seen as a failure to exercise due diligence in finding an optimal balance. Professional reasoning. Professionals should approach such situations by first understanding the core technical requirements and constraints. They must then identify and consult the relevant engineering standards and regulatory codes applicable to the specific project and jurisdiction. This forms the basis for evaluating potential solutions. The engineer should then present a range of compliant options to the stakeholder, clearly outlining the technical merits, risks, and cost implications of each. This transparent communication, grounded in regulatory compliance and sound engineering principles, empowers informed decision-making while upholding professional responsibility.